All right, so I am very excited to be talking to you about soil science and building codes. It seems far-fetched that those two things are actually related, but as we learn more and more nowadays, everything is related more than we ever thought. I am going to be sharing a lot of graphs. So if you fall asleep, you will be on the webinar and I won't know. There's a lot of graphs involved. A lot of my resources come from the Intergovernmental Panel on Climate Change. This is the board or the body that basically directs the action agreements that come out of the Paris Accord. Architecture 2030, which most likely everybody's pretty familiar with. They recently guest edited Architect Magazine's issue. It was all about carbon within our profession. And then I'm going to unapologetically do some copying with permission and giving credit to New Frameworks and the Endeavor Center. Their Endeavor Center is a environmental building school in Ontario, and New Frameworks is a design build firm that's in New England. And I'll let you know when I get to those points of the presentation. All right, our first graph. I would typically ask for raise of hands if people are familiar with this graph. I'm just going to assume that we all are. We're not here tonight to have a discussion about whether the carbon in the atmosphere is increasing or whether climate change is happening. We are just going to jump beyond that. That's a whole nother conversation. And I would love to know if people are familiar with this graph. Just maybe wave at me if you are. So this graph is also from the Intergovernmental Panel on Climate Change, the IPCC, and it represents these three lines are three potential scenarios in which we choose to act as a global society to not peak emissions, curb emissions, or dramatically cut emissions. The middle line is what we have to do to enable the planet to remain below 1.5 degrees Celsius of increase. And climate scientists have projected that we have until 2030 to make this shift. It's not a small ask or task. It is a big thing, but it is something that we are in control of. But what does architecture have to do with that? Well, from these two studies and graphs, this is on the left, we see information from the EPA, and on the right from Architecture 2030. We can conjecture that buildings have something to do, they definitely play a role in emissions and carbon in the atmosphere. We could say that maybe it's 6% or maybe it's up to 50%. But the other piece of this is that agriculture and other land use, forestry especially too, also plays a pretty big role. Industry is in there, and electricity and heat production and transportation. These are all things that we deal with within our profession. Tonight, we're going to talk specifically, rather than going down the road of like transportation and urban planning, we're just going to talk about operational emissions and embodied energy in materials. This graph shows the projection of floor area growth over the next several decades. Buildings aren't going to slow down anytime soon. We are going to be continuing to increase. And then also here we can see food demand increasing, which relates directly to agriculture and forestry. Food demand is dramatically, exponentially increasing. No sign of that slowing down anytime soon. So how are these two things related? Soil science, agriculture, forestry. and building codes. A, they are major contributors to climate change, and B, they are therefore major opportunities for carbon storage. I'm going to share this little video with you because it explains the soil and carbon storage better than I can. It's the guy in the video is a little annoying, but the graphics are very clear.
Do you feel hopeless about climate change and the damage we are doing to our planet? I did. But then I was shown a new way to look at the problem, which made the solution so obvious and so within reach. A solution that's right under our feet. Climate change is all about too much carbon in our atmosphere, but carbon's not our enemy. It's the building block of life. Everything alive is made of it. It's us. The problem and the solution are simply a matter of balance. Let's step back and look at the 5 pools of where carbon is stored on planet Earth. Starting about 500 million years ago, when plants appeared on land, carbon began to cycle in an amazing balance, a balance that allowed for life as we know it to evolve. Then one life form, us, figured out how to extract carbon from the fossil pool. Then we burned it for energy, putting it into play, disrupting that balance. The way we manage land and do agriculture is moving even more carbon from the soil and biosphere into the atmosphere. Specifically, we've moved 880 gigatons of carbon dioxide into the atmosphere, which is heating up the planet and destabilizing our climate. Now, the oceans have absorbed a lot of this excess carbon, which is resulting in ocean acidification and accelerating a mass extinction of sea life. So in order to save life as we know it, of course, we have to stop releasing fossil carbon. The big question is, where do we put this excess carbon to get this cycle back into balance? Well, remember when I said that the solution is right under our feet? It literally is. It's the soil. Plants, with sunlight and water, perform photosynthesis. They pull in carbon from the air and turn it into carbohydrates, sugars. Then they pump some of those sugars down through their roots to feed microorganisms who use that carbon to build soil. Voila, carbon moved. Plants pump it in and soil stores it. Nature's living technology is amazing. Scientists have recently discovered that applying a thin layer of compost sets up an ongoing positive feedback loop that brings more and more carbon into the soil each year. In concert with other regenerative practices like not tilling the soil, planting trees, cover crops, and planned grazing, we can build and retain gigatons of soil carbon. This is carbon farming. This is regenerative agriculture. And there is nothing more powerful than an idea whose time has come. Unlike more carbon in the atmosphere, more carbon in the ground is good for us. It makes healthy soil, which is nutrient-rich, full of life, and holds way more water. This means more nutritious food and crops that are more resilient in the face of drought. That's good news for farmers, families, and everyone that eats. Remember this, the way we grow our food, fiber, and fuel either puts carbon up into the atmosphere or it pulls it down into the ground. The regeneration of soil is the task of our generation. Our health, the health of our soils, and the health of our planet are one and the same.
Okay, so I promise this guy's not just a nerdy hippie. There are economic solutions that are following this philosophy, and I'll show some graphs that confirm everything that he's been saying. Oh, I think the video is still happening. Sorry about that. Okay, there we go. Okay, so carbon buyers, soil value exchange. There are companies out there, one of which was actually formed right here in Teton Valley, Regen Network, that have developed either relationships with governments or even like an app that farmers can use to provide incentives. It provides incentives for farmers to use more carbon storing practices. So if a farmer adds compost, for instance, they have to track that with the app and testing equipment, and then they get perhaps a stipend, or there's a better word for that, but some sort of incentive from their government. This is from the IPCC again, showing different sectors of the agriculture and forestry industry. And over here we see this is mitigation potential, storage potential annually. So again, how are soil science and building codes related? Well, the devil's in the details, and the details are the materials, things that we build them out of. Agricultural residues, anything agricultural is biogenic carbon. I'm using the term residue to refer to a waste material, something like straw or hurd. And biogenic carbon, these things can be building materials. And in fact, they are often, there are some that we use regularly, and I'll get there. This graph actually shows the potential within the mint green. Light green here is buildings, and the brown is the forestry industry, to reduce emissions or store emissions over time. This might sound like a really hard thing to do, but we have seen over the years a really big change in the pie chart of energy in buildings. 20 years ago, this is what we were doing. A lot of operational carbon was needed to keep our buildings comfortable, especially in our cold climate. And the embodied carbon was fairly small. What we have done is we have done a fantastic job of really reducing the operational carbon with improving energy performance. But to do that, we have greatly increased the embodied carbon within the buildings. So the pie might be overall a little bit smaller, but we're not there yet. This graph represents one of the ways that we have done this. We've increased our use of more clean grids and decreased use of some grids like coal. Obviously, gas is still going up. Coal has gone down, gas is going up. But we can also see that over the past, since 2015, so that's 5 years, we have begun to really reduce emissions, even as floor area has dramatically increased. And again, confirmation that we've reduced emissions since 2016. So we're doing something right. However, this graph, the yellow represents embodied carbon annually, and the blue graph represents embodied carbon annually. We can see that if the amount of buildings that we're building per year, it stays relatively the same, we're not yet making dramatic shifts in the embodied carbon in our buildings. And even though we are improving emissions over time, operational is still going up. Ultimately, we cannot net zero with energy reductions energy and efficiency reductions out of this situation. Again, we have 10 years to solve this problem. So this graph on the left is the same graph we saw before. It's what we've been doing. The graph on the right shows what we really need to do. The embodied carbon piece of the pie needs to still dramatically reduce. And if we can do this thing on the left, why not consider if we can do the thing on the right and actually become part of the planet's solution? So now I'm going to begin just copying from New Frameworks and Endeavor Center's presentation to the Northeast Sustainable Energy Alliance. I think that's what it is. I have known that at a time, but I forgot. These are the folks. We have Jacob Rakusin here of New Frameworks, Chris Magwood of Endeavor Center, and Ace McCarlton of New Frameworks. This slide explains a little bit about embodied carbon. I'm assuming that most of us know what that is. It's basically all of the emissions, energy that goes into any object over the life cycle of that object. If you have questions, please just feel free to unmute and pipe up. We're a small enough group, so there's no problem with that. So their message and my message is that we need to dramatically reduce our emissions. And in order to do that, business as usual isn't going to get us there. We need to be thinking outside of the box. We need to be thinking and connecting with all aspects of the industry within which we work. We need to consider even outside of that into eco-agriculture and be always considering social and climate justice. All right, so this just, I'm going to get into a pretty intensive study that these folks did together. And this just explains where their data came from. An environmental product declaration is a label. It's sort of like a ASTMI, shoot, I'm forgetting those words, that acronym. But we have already many types of product standards out there that we reference within the codes, within our work on a daily basis. An EPD is a new type of that kind of label that identifies global warming potential, acidification potential, basically toxic potential within the environment or to humans. And it also, the GWP basically is that embodied carbon piece. The data of these varies. Not every product out there, material out there has one of these. So, and the data definitely kind of varies. It's not as good yet as we hope it will be. Some of the data, if it's provided by a manufacturer rather than a third party, you know, it's not yet vetted. So this graph is from their study and represents the embodied carbon of some of the materials that we use on a daily basis. And there's this bizarre green one. Obviously, we don't use hempcrete vacuum panels or aerogel on a daily basis, but the others we do. And it's green and negative. What the heck does that mean? It means that that actually represents storage of carbon rather than emitting of carbon into the atmosphere. This shows exactly how that happens. Plants just do this. It's what they do. It's how they survive. It's what photosynthesis is. They store it in the plants themselves and transport it into the soil. Again, just a reminder that this is scientifically proven and agreed upon that there's a lot of potential here. So here's that slide showing some of the products that we use on a daily basis, timber and cellulose especially. The other ones not so much, but they are becoming mainstream. And these ones are not yet mainstream. And then we can also look at finished materials that they're not plant-based, so they do not store carbon, but they are either carbon neutral or have very, very low carbon impact. Lime plaster, I don't know if any of you are familiar with the lime cycle, but it does take CO2 to process lime from limestone to be able to use it. It's a really fantastic binding material, so it's great for wall coatings. It is antimicrobial, and it's basically what the Romans lined aqueducts for because it helped keep their water clean. And clay plaster, while it's, oh, sorry, I wanted to mention also that while it takes CO2 to process lime to be able to use it in this way, it then absorbs the CO2 that is used back into it to turn essentially back into limestone. And it takes a matter of months to years, depending upon the thickness of the product. Clay plaster is not using any sort of chemical reaction. It's simply clay with water added, and as it dries, it hardens. It's been used also for thousands of years as a building material. It's incredibly beautiful, and it's also antimicrobial, and it pulls moisture out of the air and releases negative ions. So it can have a mood boosting effect, as well as, in addition to mechanical ventilation, help to improve our air quality. I want to speak a little bit especially about Limestrong and relate this back to Idaho. We have a local product. Limestrong is actually manufactured in Malad, Idaho, where the Hess pumice plant is. Ryan, the owner, founder of the product, lives in Salt Lake. He's taught several tradesperson trainings in Idaho, and is willing to do that throughout the region. He will come to your project and teach. For Love Shack, he taught some drywall contractors. We had a workshop here in Teton Valley and had GCs and sheetrock folks all learning how to use it. It's very easy. It doesn't take, it's not super labor intensive. It is a little bit more than paint, but there is less masking involved than paint, and it's completely VOC free and just incredibly gorgeous. All right, so back to how these materials and building codes are related. So most of us know that a best practice of improving energy efficiency, and it's required by the code, is to implement continuous insulation. And our defaults are often blue board or some sort of polyiso with a film on it, or spray foam. And we all think that these things just are kind of a one and done, like they do everything so well. And they do work great, and there are instances where they're the right material to be used. But this graph, again, just to drive it home a little bit, not all materials are the same in terms of their impact to the environment. So here we can see the payback in years of the energy or the emissions emitted by these materials. The graph on the top shows the full range. The graph on the bottom, breaks down this other little tiny stuff that we can't quite see. So that it's related to the final R value. We're typically, for a code level wall, we're in the R20 range. That's over 100-year payback if you fill that wall with spray foam. A building is going to last maybe 100 years if we're lucky. Often it's more like 50 years. We need to really consider if we are actually achieving the end goal. Sure, we might be saving the clients some money in energy bills over the years, although the cost of that material up front is pretty expensive. There's definitely a payback period for that. But I think it's important to just ask ourselves as practitioners and professionals whether we couldn't be using these other materials that have a much shorter, much more reasonable payback to the atmosphere. Cellulose down here, like 6 months and done. So here are some alternative products to the blue board that we so often use. Gutex is probably the most common one. We're seeing it more and more commonly, and there is an American product that will be on the market hopefully within 6 months to a year. Sonoclimate is a Canadian product. Sorry, Gutex is European. I'm not sure which country exactly from. Sonoclimate is a Canadian product. This one, Insole, and I don't know what it is exactly, but it is the same manufacturer as Sonoclimate. And then I wanted to mention Hempitecture because while hemp wool and sprayed hempcrete may not necessarily be a continuous insulation alternative, they are a local product that that we can take advantage of. Hemp wool is technically manufactured in Canada, but Hempitecture is located in Sun Valley in Ketchum, I believe. Okay, so getting a little bit more into the weeds of this study. Just this text is saying that basically, okay, so we know that the materials have high carbon output, but we don't want to just make the same mistake that we may have done when we started thinking about energy efficiency. How do we know that we're making it better? How do we know that we're doing the right thing if we make this change? So this study basically takes two different building typologies, a single family residential building and an 8-unit residential building, and compares different grids as well as 4 different levels of embodied energy and materials. And right now, the first part of what I'll share is only looking at the embodied energy. We'll get to adding the grid in later. So here we see the 4, 2 different buildings, multifamily, single family, and 4 different assembly types. On the left, in the red, this is probably representative of steel and spray foam. In the blue might be steel and fiberglass. The yellow is probably wood and cellulose. And the green would be straw bale or hemp or some combination of wood and those 2 things. We're looking at kilograms per square meter of the building. And then we're also looking at code compliant versus high performance. So the difference between code compliant versus high performance, just for example, with the high embodied steel and spray foam building, you go from a not so great building in the terms of code of energy performance to a better building, and you can just see that the embodied energy increases. On the other hand, the embodied energy storage potential also increases as you go from code to high performance. The same thing over here. Of course, with single family, we're not getting any economy of scale. It takes a lot more resources to house as many people with single family units as it does with one large, more dense building. So what does this mean? What does that look like overall? We're talking about several coal plants annually. This is annual data. We are either adding 23 coal plants or removing 10 coal plants. All right, so I am going to apologize to Bruce Westerman of Arkansas for picking you out of the crowd. I want to talk a little bit about some policies that are working their way past Congress recently. I think it's called the 1 Trillion Trees Act or something like that. Trees are fantastic, but we need to maybe check ourselves a little bit. Trees are the ultimate carbon sequestration device, he says. There is no limit to how much carbon we sequester if we simply plant trees and harvest them for whatever we can do. But not all biogenic carbon is the same. And I want to come here to this slide first, because not all wood is the same. Wood is actually a fairly complex material because forests in their ecosystem store a lot of carbon. They provide habitat, biodiversity. There are a lot of very immense ecological benefits that forests provide us that might outweigh the benefit of just storing all the carbon and just sort of like farming forests. This slide right here represents the difference, however, that FSC certified wood is an embedded carbon benefit. When we are using business as usual forestry techniques that don't consider biodiversity and aren't sustainable, then we're completely negating the potential carbon benefit of harvesting wood. And then I just wanted to share this slide too. This looks at 4 different types of crops and their potential for carbon storing, or rather the carbon emitting and storage over time. So you can see this represents years, the horizontal axis, and the vertical graph represents effective forcing, which is a topic that I'm not going to get into, but basically what it represents is the carbon that's needed to harvest the product and then the storage potential over time. So we can see that with like little crops, like straw or grass, the amount that's emitted is very low, and then it just stores it over time. A eucalyptus has a higher emissions initially and then stores. Aspen, you can see, it's a bigger thing, so it's harder to harvest and get to the source. So that has a bigger emission initially. And then spruce, the same. But then it also can store more. So that conversation is just a little bit nuanced. And I hope that our politicians will consider the nuances when they're pushing policy through. This graph came from the Forest Service, and it represents that there is a lot of potentially stored, potential for carbon storage within forests, and this breaks it down by region. But again, this requires that it's sustainably done. And our practices are not necessarily across the board good at the moment. It will take some time to implement those forestry practice changes. So again, time is of the essence. And I'm going to jump into looking at straw. So 2.16 billion tons of straw were grown in 2016. That's enough to offset all current transportation greenhouse gas emissions and more than replace all current insulation materials in that year. Okay, so now we need to consider the grid, basically, and that operational emissions do still matter. We can't just forget about those. So this graph is looking back at that 8-unit multi-story building and what happens over time. So we're starting out, we built it in 2019. It takes this much energy to get it built. And then over the years, we're just adding a little bit extra operational energy. And then we're gonna look at 2051, what the overall total is. Did I have that date right? Yeah, 2051. This is, so I believe that this was maybe the worst. Oh, this was the high embodied energy building, but code compliant. So this is kind of the worst case scenario. And then this is looking at the 8-unit residential building. Sorry, I want to point out too that this is a natural gas grid. This is an Ontario grid, which is all electric, I believe hydro. So I'm not totally familiar with all of the electricity sources in Idaho or Montana or Wyoming. I know here in Teton Valley, we are all hydro. I know Jackson is hydro, so we have a really relatively clean grid. Those emissions that were emitted to build the dam, that's already done. So just showing, highlighting, I guess, or emphasizing that even a multifamily huge building like this can store carbon. All right, so this slide is getting a little more into the weeds with the numbers and looking at the operational energy use of each scenario. So we can see that in the code compliant example, we do have a higher operational energy use than the high performance one, and that's the case across the board. A high performance building with high embodied energy materials releases more emissions than a code minimum building with moderate embodied energy materials. So just to hit that home a little bit more, if we are building this building with spray foam and steel, we're not actually doing the planet all that much good. We would actually be better off to build a code compliant building. And I just want to highlight here that we're not saying that to do the right thing, you have to build a building, an 8-story building out of straw tomorrow. That's not realistic. That's incredibly radical. We don't have the systems in place to make that happen. But there is something that we can do tomorrow that makes a huge dramatic difference. And that is this thing right here. This building is built with wood and cellulose. You can get them at Home Depot. They are used every day by every contractor that any of us have worked with, except for the insulation provider in Jackson, Wyoming, who refuses to use cellulose and charges more for it. Does the grid matter? Yes, the grid matters. I might not get too much into this, but we can see that the numbers here are different from the previous graph with an all-electric grid. It's kind of just saying the same thing I said. Okay, here, this is where the grid matters. This is hugely different. This is the emissions of an all-electric grid. And then I guess this is the breakdown of that grid. So I was wrong, it's not hydro. It's primarily nuclear. High-performance buildings made from common low-embodied materials, wood and cellulose, will be nearly net zero if on the right grid by 2050. And the lowest embodied material buildings will even still be storing carbon at code minimum performance by 2050. This is a graphic produced by Builders for Climate Change that reflects some of the same data. Oh, sorry, I wanted to share that the assemblies are actually identified and called out here. So we see spray foam, brick cladding, steel, concrete, mineral wool insulation, drywall. Here we have cellulose and wood fiberboard insulation, wood framing. And here we have isospan ICFs for the foundation, foam glass subgrade insulation. This is not quite a typical product yet. We can get it, but it's expensive. Straw and wood fiberboard insulation. Straw we can get readily. We don't all know how to detail properly with it, and it is important to know that. And wood fiberboard insulation we can get regularly. In fact, I think at our company on a project in Montana, the builder had an easier time of getting the wood fiberboard Gutex product than he did getting the Roxol mineral wool board insulation. That might not be true across the board. That could be a one-off situation, but it is a mainstream product. So this kind of is a summary of what are some things that we can do now. First of all is retrofit first, rather than build a new building, and try to build with wood and cellulose from now on. Use passive climate responsive intelligent systems. We still need to be doing the same thing that we have been doing by reducing energy use. Find carbon positive solutions if possible. And then footprint and handprint. This means track it. Either track the carbon that's going into your buildings, ask for transparency from products about where it's coming from, what the carbon emissions are, what the life cycle analysis is. Even just asking that is actually really having these certifications that have begun to be more commonplace, like the Living Building Challenge and the WELL standard and LEED have really forced some changes to the industries. I'm not going to get into those changes right now, but it works. And then we also need to just think about how we're thinking about carbon storing materials. What are the opportunities versus the barriers to using these materials? Sometimes they're not affordable. We don't actually know if using these amazing straw panels from Europe is something that's going to be cost effective for clients yet. They're not necessarily replicable and scalable. I built a straw bale house myself. It's incredibly labor intensive. I would not recommend that for every single client. Existing buildings, like those are in place and it is expensive and it is often hard to justify improvements to an existing building. And then within the realm of codes and permits, there are also some barriers that I'll get into more specifically. Well, carbon pricing, that could exist. It's not in place yet. Policies that encourage innovation. There is, thankfully, a code that allows for straw bale. There's an Adobe code. There's not yet a hempcrete code. Improvements in there can offer more leeway, more freedom, more opportunities. And then this is something that our company came up with specifically while looking at a project in Teton County, Wyoming, and considering different wall assemblies that we could use. Sometimes in different jurisdictions, there might be a requirement to keep the floor plan, the square footage, at a certain scale, or sorry, a certain limit. Say 1,500 square feet for an ARU, I think, or maybe it was 1,000 for this particular project. Sometimes there are height restrictions, and those, because a client is obviously going to prioritize getting the most bang for their buck. They want the most square footage that they can get. This therefore squeezes the building envelope to the smallest that it can be. This is exactly one reason why we default to using spray foam insulation often. It's one way to meet the building code and get the client what they want for their money. We have decided that we really kind of need to champion thick walls and ask that policy be maybe rewritten or redefined so that we can still maintain the square footage limits. I think we respect that those are in place for many reasons. But if the definition requires that the square footage be calculated to the outside of the wall, then that squeezes that width that the wall can actually be. Same thing with heights. We very, very often, I would say even more with walls, default to spray foam in a roof because we can get a much higher R value with a vaulted ceiling. And so to go to a vented truss just takes a lot more space and often pushes us, or sometimes pushes us over the height limit. So if we can find ways to work with our jurisdictions to maybe get those redefined and alert them and educate them about the environmental impacts of these materials, we can more freely at least use a vented truss roof and at least have a thicker wall with the same R value of, a double stud wall with cellulose or even fiberglass, which is a lot better than spray foam. All right, I already mentioned affordability, replicability and scale, existing buildings. So another thing we need to think about is how we're sourcing carbon storing materials. I know the Teton County Solid Waste District or Department over in Jackson, Wyoming, their construction waste is increasing a lot. I think they said it nearly doubled last summer from the summer before. They're a transfer station. So being able to reduce that waste has a benefit in multiple ways. A, it's a source of carbon, it's a source of materials, and B, it helps out with just putting that place somewhere. The space on Earth for trash is limited. We don't currently have innovative ways to reuse that trash. I've heard of a company in Portland, Oregon that is based on that principle, sourcing construction waste from the landfill or transfer stations and reintegrating it into the construction industry. Agricultural residue, like I mentioned, straw, hemp hurd, factory grown, that would be mycelium. So essentially factory grown agricultural products, mushrooms is one example. And then forestry products, bamboo, CLT, wood fiberboard, which I believe is from recycled wood. These are all things that we need to there are opportunities to implement more often. Just want to check the time. So it's, all right, it is 7:30 almost.
And Lindsay, I was going to let you know that we do have a couple of comments and questions.
Oh, great.
When you're ready, I guess. I'm not sure if how close you are to closing out the presentation.
Yeah, I think the only other thing I would want to get into might be some examples of projects that use these materials that are modern and aesthetic and not sort of like the DIY hippie kind of project. But I think that answering questions is more important. So let's do that.
Well, we just had a question from Lotus about comparing magnesium oxide boards as an alternative to gypsum board, as an example of, how to replace really typical materials with something that might just be a better choice as long as the sourcing is there.
Yeah. So I recently kind of fell in love with magnesium oxide board. Although I've never handled it personally, but I just have been seeing this more and more information about how easy it is to work with, how the stiffness of it enables you to have less framing. It's less labor intensive. It's very easy. It's like one coat of material, a light sand, and you're done, instead of the layers of drywall, taping and mudding that has to be done. The embodied carbon of magnesium oxide board, unfortunately, is really high. It's quite a bit more than drywall. So you have to ultimately use a life cycle analysis tool, a carbon calculator tool, to calculate the benefit of using this magnesium oxide board, which would save you in framing, and balance it all out. My gut is that the magnesium oxide board is probably high enough that the savings in framing doesn't outweigh the extra energy needed to manufacture that product. But there are always tons of factors in a project, such as time savings and cost and labor, and it's never an easy answer. Lotus, does that answer your question sufficiently, or do you have?
Yeah, I was just curious to know more about it, and thought this would be a good opportunity to do that.
Cool.
We have another question from David. Is commercial cork flooring an energy embodying sustainable material? Do you have any insight or feedback about the commercial cork flooring?
Cork is fantastic. Cork definitely stores carbon. Of course, we'd have to look at the particular product and see if it has an EPD and if it has some of this data available. But my gut is that anything that is a plant-based product is most likely a good product to use. even if it is manufactured and even if it is coated. The toxicity of the coating, that's another question, another story.
Great. Well, I, for one, would be really excited to see some of these project examples. I know one thing that we deal with a lot in working in the sustainable space is the assumption that there's like a certain aesthetic to natural building that just really feels really particular around like an older time period, maybe less refinement, found objects, and just more of a wabi-sabi, which there's times and place for that and we love it, but I always like when natural materials become used in a way that looks like more conventional construction. So I'd love to see that.
All right, so I just wanted to take a moment to show this crazy thing. Not a conventional project at all, obviously just sculptural, but I think we can see that there's a potential here. These are mushroom bricks produced by, dang it, I don't have the name of the manufacturer here. I could look that up. I'll just, actually, I want to point out here that heat pumps, refrigerants have extremely high embodied energy, probably higher per amount of material than spray foam or XPS. So that is another thing that we need to keep in mind. I don't think the data is out there yet, though, for HVAC systems. Lotus actually used to work for this guy. Larry Strain is an architect in the Bay Area, and he says what you save matters, what you build matters, and what you save matters more. All right, so here is a project that the Endeavor Center did up in Ontario. Let's see, so the design was something that could be scaled over time. That was one of their priorities early on. Could also just be a single family building standalone. It needed to be scalable and panelizable, so it is panelized. They actually also built and took apart and rebuilt this building several times before putting it on its final foundation resting place. This is my own house that I'm sitting here in Teton Valley. The might not be the most modern example, but the straw came from Twin Falls. I used a dense packed cellulose roof. The clay on this wall and this floor came from a canyon 8 miles away. I processed it here all on site. The wood, not the engineered horizontal members, but all of the vertical members were milled from standing dead forest right around here. I don't recommend anybody to ever do that. The real rough sawn 2x4s were a pain to work with. But there's a huge story behind this building. And these materials also embody this, they can also be very modern and clean, and I don't think devoid of soul ever, but you know, there's a hand-built touch to it, even though none of us building this house were really like fine craftspeople. There's still a story to it, and it feels, just has a different feeling. The deep walls and the light coming through, the feel of the clay, it's a different thing than our typical product that we see. So this is a very conventional project. Our company did this a couple years ago, and it's double stud walls with cellulose and a vented truss roof. This is an example of a large-scale straw panel building in Europe. This is the panels being fabricated. And they're basically, I didn't always understand this, but straw panel buildings are basically built as a double stud wall. I would say the same of hempcrete. It's a double stud wall. You've got conventional framing pretty much, and then they're using a continuous insulation fiberboard panel on the exterior like Gutex, a rain screen, and then you can apply whatever cladding, whatever finish you want to. And the roof, of course, the walls, you know, are only one small part of any building. The walls, the foundation, the floors, in any of these buildings are still probably pretty conventional. Another large building. Echo Cacone is another example of a manufacturer in Europe. They just finished their first United States project. All right, and now I wanted to share some resources that I've used not only to create this presentation, but that I've learned from throughout the years. Healthy Materials Lab from Parsons New School of Design is a really great resource to learn about what products are out there that can be used. They just have a great library, and they have a lot of information about all of the certifications that go with material health and human impacts and environmental impacts. The Carbon Leadership Forum is an organization that spans a lot of different industries. It's not just architecture or engineering. It is, it's architecture, it's engineers, it's designers, it's carbon experts, people who run the certification programs, the USGBC Living Building Challenge, it's the Forestry Council, it's, I haven't seen any farmers on there yet, but there are builders and entrepreneurs. Anybody can join it. If you go to this Embodied Carbon Network here and click on that, you can, that takes you to the Carbon Leadership Forum, which is basically a forum of conversations. Architecture 2030, which again, we probably already know about, but they developed this carbon materials, carbon smart materials palette. And it's not completely comprehensive, but if you have a material you're interested in using and you want a crash course in it, go here and look up, say, CLT or straw or hemp, and it will give you all of the basics that you need to know and resources about how to use that material more specifically. And then newsociety.com, they've produced this great series of books that our company uses often. More general, like building science, to how to use many of these different materials. Other architecture firms, we love working with our other architecture firms. We hire other firms to consult for us and vice versa. Hempitecture also is a design resource for you, for architects and builders. Okay, 475.com. These guys are the bomb. They are experts in building science. They are advocates. They provide the best material products, and they provide them very quickly and easily. They are a source for Gutex. Lotus and Lindsey, you want to hop in here? Like, we use them on a daily basis, pretty much. They're consultants.
Yeah, I would just add that, when we've had questions about materials and we've been going through systems that are new to us and applying them for the first time, even if they've been tested and proven in other markets across the country in similar climates, they've been really, really willing to help us with education and specification. And I have not worked with a products company that gets so invested in training the professionals that spec their products. And it's not just, really strict proprietary stuff. There is a lot of information from 475 that is not just about, here, let me sell you a product. It is really about building science. So I encourage you guys all to sign up for their newsletters. It's one of the few newsletters and blogs that I actually read these days.
They have free details. They have free assembly guides that you can just download. Super awesome. Okay, I am kind of forgetting this climate smart construction one. Sorry, that might have been the end. This is not about professional women. This is on LinkedIn. That's the only place it exists. And I believe it was started by the forestry industry. And to me, it kind of seems like their own little version of the Embodied Carbon Network or the Carbon Leadership Forum, which technically are one and the same, but more specific to forestry. And they have encouraged anybody to join. And so I'm sure there are a lot of resources and good conversations on there. All right. We made it through, and I think we lost a few people, but not everybody.
Hey, Lindsay, are you going to be able to share this presentation afterwards?
Yeah, good question. Jonathan, I would ask either you or Nikki if you're willing to share it to AIA East Idaho.
Yeah, we can definitely do that. No problem.
I didn't mention CEUs at all, but there is a form that I think everybody received with the invite from Jonathan. And anybody else, if you want it, I could share my email address in the chat, and you can just email me and I'll send it to you. Or I guess another thing we could do is everybody could just type their email in here. I don't care. If you want to avoid emailing me, then just type it in to the chat, and I won't close it until I copy and paste it.
So Lindsay, will this just be a self-report CEU event, or are you submitting it?
Jonathan, can you help me out with that? Do you?
That is a great question, actually. I don't know how you want to handle that, or how we should be handling that from our end if we need to do something.
I suspect that if you just sign the form and does everybody know Anna Foster at AIA Idaho? Of course, you can't answer me all at once.
Yes.
Sorry, I'm still treating this like a classroom or a conference. Here, this is what I'll do. I'll type Anna's email into the chat. That's like the most efficient thing. Okay, stop sharing.
Also, Lindsay, we'll have, since we've been recording the meeting, we also have a list of everybody that was present for the presentation, so we can verify for Anna who participated.
Yeah. Yeah, for that. Okay. Anna Foster at AIA Idaho. And I've got Anne Wozniak, I'm probably saying that wrong, but I've got your email, and Morgan's. Cool. All right, well, thank you so much for joining, everybody. I hope you got something out of it. If you have any questions, moving forward in the future about how to implement any of these materials, don't hesitate to reach out. We'd be happy to have a chat about it, or point you to a research, a resource that might be more timely and more helpful at the moment for you. Okay, I've got Brent Davies also and Richard Youngblood.
Perfect. Well, Lindsey, we really appreciate you taking time to do this and present this to everyone, and really, really good content. That was awesome. So thank you.
Thanks. I hope it wasn't too many graphs and put everybody to sleep. I have no